Welcome back to this tutorial. We can discuss about the 2's complement arithmetics, basically the addition and subtraction in this video. Okay, and we can start with the addition. And here I am using this particular table that we have derived in our previous video. This is the 2's complement representation of binary numbers that can be represented using 4 bits. And one thing I need to say you that you don't want to mug it up actually. Okay, you don't want to remember all these 2's complement representation in your mind, but for better and fast and error-free calculation, try to remember the 4-bit representation of binary numbers. That is the 4-bit binary representation of values from 0 to 50. If we know the binary representation corresponding to numbers from 0 to 15, then it will help you to calculate fastly, and you can generate 1's complement and 2's complement form easily without error. Okay, for converting or for getting negative corresponding values, we can follow the rule for converting into 1's complement form and 2's complement form. That is enough. You don't want to remember all these values. Okay, so now we can start the addition of numbers in 2's complement form. Okay, for better explanation, now I am using this table directly here. Okay, for more clarity. So here this is the case of addition. We want to add two values, positive 3 with positive 4. And for adding in 2's complement representation, you are asked to add two binary numbers, binary of 3 with binary of 4, which is in 2's complement form. For adding such value, what we want to do, directly add these binary values. This is the corresponding 2's complement representation of positive 3, right? And this one is the 2's complement representation of positive 4. And the important point is, for the positive numbers in signed magnitude representation and 1's complement representation and in 2's complement representation, the representation for positive numbers are all the same. Okay, but the 2's complement representation for negative number is not equal to the 1's complement representation of the same negative number. Okay, the negative numbers may have different representation in 1's complement form and 2's complement form, but the positive numbers are, or positive numbers having the same representation in 1's complement form, 2's complement form and unsigned magnitude form. Okay, so we can add these two directly. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1 and 0 plus 0 is 0. Here we have no external carry. Okay, so this is the result of our addition, and this is equivalent to, or the value of this particular result is, from this table it is 7. Okay, so the expected answer is also 4 plus 3 is 7. So the answer is correct here. Next, another addition. Minus 3 plus minus 4. We need to add two different negative numbers. One is minus 3 and next is minus 4. For adding these two minus numbers, takes its 2's complement representation. Minus 3 is from this table. We can take directly from this table, that is 1101, and for minus 4 it is 1100. If this table is not here, we can generate the 2's complement representation of minus 3 and minus 4 by following that particular 2's complement conversion principle. What is it? Take the representation of positive 3, then take its 1's complement and add a 1. Then it generate the 2's complement representation of minus 3. Okay, so using that or following that method, we can generate negative numbers 2's complement representation. No need to remember this table. And for the explanation, now we can use this table. Okay, minus 3, this is the 2's complement representation, minus 4, this is the representation. Now we can add these two. 1 plus 0 is 1, 0 plus 0, 0. This 1 plus 1 is 0 carry 1. Okay, that carry 1 is added with these two ones. 1 plus 1 plus 1 is 1 with carry 1. Okay, if such a carry occurs in case of addition, in result if such an external carry out occurs, we can simply discard that carry. And the remaining bits of the result form the result of our addition. Okay, so here minus 3 plus minus 4. In decimal, while adding these two, we get an answer minus 7. So here we generate a binary representation after this addition, that is 1001. From this table, 1001 is minus 7's 2's complement representation. So answer is exactly matching with our value, expected value. So the answer is also correct. So this is the rule of addition. That means after addition, here we have no external carryout, right? So the generated result is the generated result itself is the correct expected answer. And in this case, after addition, if it generates a carryout, then we need to simply discard or drop that carry. And the remaining bits of addition or the remaining bits of our result form our expected result. Okay, this is the case of addition in 2's complement form. Okay, now we can consider the subtraction. So subtraction can also be represented in terms of addition. That is, a minus b can be represented as a plus 2's complement of b. Okay, for any subtraction, we can perform that subtraction like minuend plus the 2's complement of subtracted. This will generate the exact result of this a minus b. Okay, if you are given two binary numbers and you are asked to subtract one from another, then what we want to do? Take the 2's complement of our subtractant and add that value with our minuend. This will generate the exact result of a minus b. Here we have one procedure for performing this subtraction. That is, first find the 2's complement of our subtractant. Then it is added to the minuend. Here b is the subtractant and a is the minuend. Okay, so find the 2's complement of b. A minus b means a plus 2's complement of b. Okay, so find the 2's complement of b. 2's complement of b is the minus form of positive b. Okay, that is a plus of minus b. Okay, so this minus b is the 2's complement of positive b. So find the 2's complement of positive b, that is added with our minuend a. Then after the addition, check or analyze the result. If a final carry over or the final carry out occurs in the sum value, if the final carry out equal to 1 in the sum value, that means from this we can conclude that the result is positive. If there exists a carry out in the sum value, that means the result is positive. We can simply discard that carry out and the remaining bit generate the magnitude. Okay, and if there is no carryover, that means there exists after addition, we don't have any carry out value. From this, we can conclude that the generated result is a negative value. And in order to get its decimal equivalent or get the value of that result, what we want to do, takes the 2's complement of the generated result. So this is the procedure. Take the 2's complement of subtractant and add with the minuend and check the result. If there exists a carry, then we can conclude that the generated result is positive. Simply drop that carry out and the remaining bits gives you the magnitude. And if after addition the sum contains no carry out value, In that case, we can conclude that the generator result is negative. To get the value, what we want to do, take the 2's complement of that sum value. Okay, consider some example. Use the same table here, using this table here for explanation purpose only. Okay, consider this 4 minus 6. We can consider this subtraction as 4 plus minus 6. Okay, 4 from this table is this 0, 1, 0, 0, and minus 6 is actually the 2's complement of 6. 2's complement of 6 is minus 6, that is 1, 0, 1, 0. Now we can add this. Positive 4 is 0, 1, 0, 0 with minus 6, 1, 0, 1, 0 in 2's complement form. So after addition, this is 0, 1, 1, 1. This is the case. Here we have no carry. No carry means the result is negative, and this bits 2's complement form decide the magnitude. Okay, what is the 2's complement form of this 1110? 1110 is actually minus 2. Minus 2's complement form is actually positive 2. Okay, so this is 0010. In another way, how to get the 2's complement form of this particular number directly? We have a shorthand method, that is scan from right end and proceed towards left and stop there when a 1 is found. So stop here and write the bits up to this 1 as it is, that is 0 is 1 is kept as it is here, and complement remaining bits after the first one. So complement these two. So these two ones become 0, 0 here. So this is minus of 0, 0, 1, 0. 0, 0, 1, 0 is actually, the value is actually 2. So the result is minus 2. Okay, consider another example, minus 4 plus 6. This is the case of 6 minus 4. Right? So we can represent like this, 6 plus minus 4. 6 is this. Okay, its binary is 0, 1, 1, 0. Or its 2's complement form, or the binary representation, all are the same. So we can consider this 0, 1, 1, 0. The sign to magnitude representation of positive numbers, 1's complement representation, 2's complement number representation, all are the same for positive numbers. Okay, so 6 is represented like this. And for negative 4, what we want to do? We can consider the representation of positive 4, then take its 2's complement form. Now it is directly available from this table. So we can directly take from here, take from this table 1, 1, 0, 0. So now we can add 0, 1, 1 plus 1 is 0, carry 1, that carry is added with these bits. 1 plus 0 plus 1 is 0, carry 1. So in this addition, after the addition in the sum, we have the carry out value, the fifth bit. Right? So this is actually the carry out value. If such a carry is available in the result or in the sum value, we can conclude that the generator result is positive. And simply drop that carry and the remaining bits gives you the value of the sum. Okay, so this is actually 0, 0, 1, 0 means this is 2. This is the binary equivalent of our 2. So the result is positive 2. Okay, consider another example, that is minus 8 plus 3. So we can represent like this, 3 plus minus 8. Okay, that is minus 8 plus 3 is actually 3 minus 8. Right? It can be represented like this, 3 plus minus 8. The representation of 3 is 1, 0, 0, sorry, 3 plus minus 8, 8 is also equal to minus 8's 2's complement representation, sorry, minus 8's 2's complement representation plus representation of 3, right? So minus 8 is actually 1000. We can add this with this 3. 3's representation is 0011. Okay, so while adding these, we get 111101 with no carry here. If no carry is available in the sum value, carry means the fifth bit here. Here we have no fifth bit. So in that case, we can conclude that generated result is negative, and the 2's complement of this gives you the value of sum. Okay, so how to get the 2's complement form? Scan from this position towards left and stop when a 1 is found. Here in the first location itself 1 is available. So stop there and write that 1 as it is here and complement remaining bits after that first one. So this 1 becomes 0 here, this 0 becomes 1 here, this 1 becomes 0. So this minus of this. This is actually our 5 binary. So the result is minus 5. Okay, another example. This is 7 minus 3. This can be represented as 7 plus minus 3. 7 is this and minus 3 is 1101. Okay, or we can take the positive 3's binary representation and convert it into 2's complement form. Okay, this is directly available here in this table. So we can take from this table now. That is 1101. So after addition, this 1 plus 1 become 0. That carry 1 is added with this one. 1 plus 1 plus 0 is again 0 with a carry to this level. 1 plus 1 plus 1 is 1 with a carry. That carry is added with this level. 1 plus 0 plus 1 is 0 with a carry. Here we have fifth bit. That is a carry out here. Okay, if such an external carry out occurs, what we can conclude? We can conclude that the result is positive and the value of that result is obtained by discarding this carry out value. That is positive of 0100. 0100 is actually positive 4. 7 minus 3 is positive 4 itself. So the exact expected answer. Okay, so this is the case of subtraction. So consider the same subtraction with 5-bit numbers, right? Using 5-bit numbers, what are the range of values possible with this 5-bit numbers? Using this expression, apply our number of bit equal to 5. So we get the value like this. We can represent using 5 bits in 2's complement representation. We can represent a range of values from minus 16 to positive 15 only. Okay, so now we can consider different example for understanding the subtraction more clear. Okay, so for getting different binary representation, we can use this positional values. You don't want to by heart all the binary representation of different numbers. Using this positional weightage, we can generate the binary easily. Okay, here it is the 5-bit representation. The fifth MSB bit represent the sign and the remaining bit decide the magnitude. Okay, so this is in 2's complement representation. The positional weightage is like this: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and last is a magnitude. Sorry, last position indicate the sign. So here we need to represent negative. This is because of this particular representation, minus of 2 to the power 4. Okay, and the values, the first bit with weightage 1, 2 to the power 1 is 2, and with third bit the weightage 4, and for the fourth bit the weightage 8, and here the sign bit the weightage is minus 16. So using these positional weightage, we can generate any of the binary numbers representation that available in this particular range. How? Consider one example. Here we want to perform 5 minus 11. That is 5 plus minus 11. Okay. So minus 11. How to get minus 11 from these weightage? Minus 11 is actually minus 16 plus 4 plus 1. 4 plus 1 is positive 5. Minus 16 plus positive 5 is minus 11. So put 1 here in this location. In this location, here and here. And remaining 2 location kept with value 0. So this is the binary representation in 5-bit for minus 11. Okay. Next, for the representation of 5, positive 5 in 2's complement form using 5-bit. Positive 5 means the sign bit is 0. So we can directly put a 0 here. And using the remaining positional weightage, 4 plus 1 is actually 5. So here we can put a 1 and here also we can put a 1. Okay. So this is the 2's complement representation for positive 5 using 5 bits. Okay, so using this, we can now using these values, we can add these two and get 1 plus 1 is 0 and the carry is passed to next level, that 1 plus 0 plus 1 is 1 and this is 1 plus 1 with 0 carry 1, that 1 is added to this level, 1 plus 0 is 1 and here 1. So here we have no carry out. So based on our procedure, if no carry exists in the sum value, the result is negative and the 2's complement of this indicate or gives you the value. Okay, the 2's complement of this is scan from right to left and stop here and write as it is the 1 0 and complement the remaining 3 bit. The 0 become 1 and these two 1 become 0. Okay, so now consider the positional weightage of these values. This is positional weightage with value 1, here 2, here 4. Okay, so here we have only 2 ones in these two positions. The positional weightages are like 4 and 1. So 4 and 2. Okay, 4 plus 2 is 6. So minus of 6. This is the value corresponding to this binary representation of sum. Okay, consider another example. This is minus 5 and this is positive 11. This can be represented like positive 11 plus of minus 5. How to generate the binary representation or 2's complement representation for this positive 11 in using 5-bit, using this positional weightage. Okay, using this, how to get positive 11? Positive 11 means the sign is 0. We can directly put a 0 here. And using the remaining weightages, how can we get the magnitude 11? 8 plus 2 plus 1 is 11. So put a 1 here in this position and put a 1 here in this position and put 1 here in this position. Okay, so this is the binary equivalent or the 2's complement representation for positive 11 using 5 bits. And similarly for this minus 5. Okay, for this minus 5, how to get the binary representation or the 5-bit 2's complement representation? So the result is, if the carry out is 1, that means we can conclude that the result is positive and the value is obtained by the remaining bits. After dropping the carry out, the remaining bits decide the value. The remaining bits are like 0 0 1 1 0. Okay, the 0 0 1 1 0, What is the value of it? Zeroth, first position with value 0, then 1, 1. 4 into 1 plus 2 into 1. 4 plus 2 is 6. Okay, so positive 6 is the value of this sum represented like this in 2's complement form. Now we can consider the overflow conditions while performing 2's complement addition. Okay, and for better understanding, we can consider numbers that can be represented using 4 bits in 2's complement form. Okay, using these 4 bits, these are the total possible values that we can represent it here using this 4 bits. Okay, so the range is calculated using this particular expression using this. This is the range of values available using n equal to 4. That is minus 8 to positive 7, and these are the values listed here in this table. Okay, now whenever this overflow or underflow condition occurs by performing addition. Okay, suppose the numbers are like this. A positive number is added with another positive number, or a negative number is added with another negative number. In these two cases, we can expect overflow or underflow. This case sometimes causes an overflow case, and this sometimes cause an underflow condition. And these two, that is, one is positive and the another is negative. That means this is the case of subtraction actually. This never cause underflow or overflow. So in these two cases, sometimes it generate overflow here. If both are positive number, then sometimes it cause overflow condition, and if both are negative, sometimes it generate underflow condition. What is this overflow and underflow? Here using this n equal to 4 bits, we can represent values, and that values ranging from minus 8 to positive 7. That can be calculated using this particular expression, and these are the possible value and their corresponding binary representation in 2's complement form here. Okay, so if this addition generate a value that is greater than this positive 7, then we can represent that value in its 2's complement or in binary form using this 4 bit. We need, if a value that is positive 8 or positive 9 and so on, we need a minimum of 5 bits. Similarly, after this type of operation, a negative number added with another negative, sometimes it generates a value which is less than this minus 8, like minus 9, minus 10, etc. Then in that case, we can't represent that particular value using 4 bits. That representation require a minimum of 5 bits. That cause underflow cases. Okay, so consider some example. This is positive 3 plus positive 4. From this table, positive 3 representation is this, positive for this. So after addition, we get a result like this. 1 plus 0, 1, 1 plus 0, 1, 0 plus 1, 1, 0 plus 0, 0. Okay, this is the 2's complement representation for positive 7. Okay, this positive 7 comes under this particular range. So here we have no overflow, right? And here, this is minus 3 plus minus 4. Minus 3 is this and minus 4 is this. So after adding, we get a value, and here we have a carry out. So simply discard that carry and remaining number. We are expecting the result as the remaining bits after dropping this carry out value. Okay, this 1001 is actually minus 7. Here minus 3 plus minus 4 is actually minus 7. That is the expected value. And here after dropping this carry out, this representation indicate the 2's complement form for this. Sorry, the 2's complement representation corresponding to this minus 7. So answer is exactly matching with the value of minus 7's 2's complement representation. Okay, here the value, the result minus 3 plus minus 4 is actually minus 7, which comes under this particular range. So here no underflow. Now consider another example. Plus 5 plus 4. 5 representation is this, plus 4, 2's complement representation is this. Okay, the expected result is the representation for positive 9. Is this positive 9 present in this particular range? No, this is not. Comes under this particular range of minus 8 to positive 7. Okay, this range is used here because we are considering number representation with number equal to 4 or number of bits equal to 4. That is why the range of values comes under this particular range. But the sum value is here positive 9. This is not available in this particular range. We need a minimum of 5 bits for representing the 2's complement representation for positive 9. Okay, so here after this addition we get a value this 1 0 1 1 0 carry 1 1 plus 0 is 1. So now consider this result 1 0 1 1. Here we have no overflow. Sorry, here we have no carry out. So the result is the bits itself. This obtained number itself. This 1011 is 1011 is actually the 2's complement representation of minus 5. Right? But our expected result is the representation for positive 9. This is not possible here using this number of bits equal to 4. So this is a case of overflow. In case of overflow, this type addition generate wrong answer. It will generate an answer, but the answer is not matching with the expected result. That is, the generated result is a wrong value. Okay, so another case. Minus 5 plus minus 4. The expected result is minus 9. This is not available in this particular range of minus 8 to plus 7. Minus 9 actually comes as a less value than this minus 8. Okay, so this particular addition generate an underflow condition. So this addition, the value generated like this with a carry out. Okay, so after removing this carry, the expected sum value is this based on our addition rule. Okay, this 0 1 1 1 is actually positive 7. This is not our expected result. We need a representation for minus 9. This is not possible. The representation for minus 9 in 2's complement form using 4 bit is not possible. So the generated result is wrong. This is because here we have this underflow condition. Okay, so our task is to identify when this overflow condition or underflow condition occurs, or whether the generated result is correct or the generated result indicate an overflow or underflow condition. Okay, for that, consider the same previous 4 cases and we can generate an expression for understanding whether the generated result is correct or whether it indicate an overflow or underflow condition, and that expression is based on the sign bits. You are asked to add two values. The first one, minuend is represented as A and subtractant is represented as B. Okay, and A, small a is the sign bit of our minuend and B means the sign bit of our subtractant. And here this R indicate the sign bit of our sum value. Okay, using these sign bits we can generate an expression like this. A bar into B bar into R plus A into B into R complement. Okay, and if after this calculation, if the generated value equal to 0, then we can conclude that no overflow or no underflow. And if this generated value is equal to 1, this indicates an overflow or underflow. Okay, so based on these examples here, the sign bit of A is 0, sign bit of B, the second Subtractant is again 0 with next this some value with sign equal to 0, that is r equal to 0. So apply this value over this expression a complement and b complement, that is 1 into r directly, that is 0, plus a and b are 0, 0 into 0 into b complement, sorry r complement, that is 1. So 1 into 1 into 0 is 0, 0 plus here also 0, 0 plus 0 is 0. So case 1, if this expression returns value 0, no overflow and no underflow. Okay, now consider case 2. Here the sign bit is 1, a equal to 1, small b equal to 1, and this is the carry out and this is the sign bit of result, and r equal to again 1. So here a complement into b complement into r plus a into b into r complement. That is 0 into 0 into 1 is 0 plus 1 into 1 into 0 is 0. 0 plus 0 is again 0. Again no overflow or no underflow. Okay, in case 3, a sign 0, b sign 0 and result sign 1. Using this a complement and b complement 1 into 1 into r, that is 1, plus a into b into r complement 0 into 0 into r complement is 0, that is 1. This term is 1, this term is 0, 1 plus 0 is 1. Okay, if this expression returns 1, this may cause overflow or underflow. Okay, so in this case either overflow or underflow is present. Okay, so case 4, sign bit is 1 here, sign bit is 1 here, and here this is the carry bit, the fifth bit, and the fourth bit is the sign bit, here it is 0. So a complement b complement r plus a b r complement, 0 plus 1 is 1. Again case 4 also a case of overflow or underflow. Okay, so using this expression we can understand whether the generated result is correct or whether it indicates overflow or underflow condition. And again, we can understand whether it is an overflow or underflow using this. In case 3 and case 4, we can distinguish whether it is an overflow or an underflow based on this last two bits, the carry out bit and sign bit. Okay, here we have no carry out and the sign bit is 1. So that is 0, 1. Okay, the carry out and sign bit combination is like 0, 1 in case of this, that indicate an overflow. And the carry out is 1 with sign bit is 0, that indicate an underflow like this in case 4. Okay, so keep this expression in your mind and this particular combination. This will help you in certain competitive exams. Okay, thank you.